Hello, everyone. It's great to be with you here today to celebrate the 10th anniversary of the Seattle 2030 district. We've come a long way together, as you will see by the presentation I'm about to make. I want to talk about the 2030 districts and put them in a global context and talk about why they're so important today. In 2011, Brian Geller had the seed actually for the first 2030 district. So Seattle became the first 2030 district, formed in 2011. Today, there are 23 districts in cities across the US and Canada. And these cities, as you'll note, are really the leading cities in terms of decarbonization and moving the building sector to address climate change. Now, all the districts have one thing in common. They meet district-wide, or they're committed to meet district-wide goals. And you'll note that it's a 50% reduction by 2030 in building energy use, water consumption, and transportation emissions. Why is that 50% by 2030 so important? Well, in 2021, the IPCC came out with its climate change report and talked about meeting the 1.5 degrees C limit set by the Paris Agreement in terms of global warming. And you'll see here to have a high probability of meeting the 1.5 degrees C, it's staying at 1.5 and not overshooting. To have a 67% chance, we have a carbon budget from that time of 400 gigatons of CO2, and to even do better, to have an 83% probability, we would limit ourselves to about 300 gigatons of CO2. So where are we now? Well, we emit roughly 40 gigatons of CO2 a year. We hear everybody talking about phasing out CO2 emissions by 2050. That's 600 gigatons. So that gives us only a 50% probability, a less than a 50% probability of staying at or under the 1.5 degrees C. So those aren't good odds. Well, what about that 50% by 2030? Well, here's a 50% reduction by 2030 from today's levels. And if we follow that line down, if we continue along that path, we will get to zero emissions by the year 2040. That gives us a 67% chance of meeting the 1.5 degrees C, of actually staying within the boundaries of the Paris Agreement. And if we get a 65% reduction between now and 2030 and phase out by 2040, then we'd even go beyond that and get closer to that 80% probability. This is the way we normally see emissions in the built environment. We have building operations is 27% of total global emissions, transportation 23%, and industry is 43%. And that's everything in industry. That's building infrastructure and substructure, the enclosure, finishes, equipment, HVAC equipment, systems, and everything else that's made in the world, including agriculture, falls into the industrial sector. And that total sector is 43%. So we've carved out of the industrial sector buildings and infrastructure, things that we're responsible for. So building materials and construction is 10% of total global emissions. And all the other, the infrastructure, the site work, things that go along with the building sector are responsible for another 10%. So you could see that the building sectors and the built environment, everything that goes along with the building sector that's influenced by the building sector, is responsible for close to half of all global CO2 emissions. This is our current our current codes, ASHRAE 90.1 2019 and the 2021 IECC appendix, which contains the zero code. So if you meet just the 2021 IACC or ASHRAE 90.1 2019, I'm going to show you where we will be in a 100,000 square foot office building. This is a typical office building in Seattle, Atlanta, Kansas City, and Boston, pretty much all over the world. They use roughly 90 to 100,000 BTUs a square foot a year. So this is from CBEX 2003. We're doing a little better now, but this is where it was in 2000. If we use the latest code standard, then this is where we would actually be, down in the 20 to 30,000 BTUs a square foot a year range. That's just meeting the code. The codes are really good now when it comes to efficiency. And if you look at Seattle, you'll see that Seattle actually is a little better. It's the darker bar from just meeting ASHRAE 90.1. So we would do roughly 20% better. So that's in the dark bar, 20,000 BTUs a square foot a year. If we take out the plug load, there's not much left in a building in terms of efficiency to get its energy consumption down. So we're doing really well with our codes. So if we just meet the codes, you're way down 75%, for example, in Seattle from a typical building or the benchmark that we set a while back. And these are the benchmarks. We said that to meet the 2030 challenge for new buildings, we should be roughly 80% below CBEX by the year 2020. And if you meet the current code challenge or the current Seattle code, you are very, very close to that 80%. You do a little bit more and you'd be at the 80%. So the current Seattle code is actually very good. And the current national code standards are really excellent. However, just meeting the code is not good enough anymore. We have squandered a number of years. We need to move the target up that we set in 2015, the 2050 target up to 2040. So we need to meet that 50 to 65% and then phase out by 2040. And to do that, we need new buildings to come in at zero carbon, essentially at zero carbon. Rather than the 80%. And that's not difficult to do. If you meet the code, you're 80% of the way there. So the first thing to do is just meet the code and try to do a little better. Use passive heating and cooling systems, daylighting, controls, more efficient equipment when you can. You can always do a little bit better than the code, but just design an efficient building. And if you meet the code, you will automatically do that. And then what we say is design all electric and produce electricity on site when you can, where you can. Solar is now much, much cheaper than any other energy source. And then if you can't, then bring in offsite renewable energy. Make sure that the energy you're getting is produced by renewables. If we do that, then all new buildings are zero carbon buildings, and that's what we need to strive for. Okay, so the codes are getting there, are getting us very close to zero, and then if we go all electric and use renewables for electricity, either on-site and or off-site, then we're at zero. What about all the construction materials when we build buildings? And the infrastructure, the site work and everything that goes along with buildings. There are literally hundreds of thousands, millions of products that we can choose from. So how do we get a handle on that? Well, here's the pie I showed you on where all the emissions are. And I'm going to reshape this now so we can get a handle on this industrial sector. If we reshape the pie and we look at the total industrial sector, we see that just two materials, concrete and steel, are responsible for just about half of all industrial emissions. If we add in aluminum, we go greater than half. So essentially two materials. We got to get a handle on steel and concrete, and then all the other materials and the industrial sector. But we need to focus on steel and concrete immediately. That'll give us huge, huge reductions. And we can do that. We see in a building, the structure, just the structures, concrete and steel, in most building types are responsible for from half to roughly 3/4 of all the building's embodied carbon emissions. And if we save a building and just redo the interiors and possibly the skin, that's the most conserving in terms of building design is renovating existing buildings. So now, what do we do? Well, we need to change the conversation. And the conversation is changing. We need to focus that conversation on steel and concrete right away. And we're beginning to see that actually in mainstream media. Concrete, the most destructive material on the planet. Steel makers next in the crosshairs as climate pressure grows. So we can see this happening. And there's an alternative. The more wood and cross-laminated timber, mass timber, glue laminated timber that we can use in a building, if we prioritize that, then the more pressure we put on steel and concrete to change. They're starting to get heartburn right now by losing market share to wood. So the more we do that, the better off we are. So it provides an alternative. And as we know, wood is a beautiful material when used in the right way and exposed in structure, et cetera. So what are the three things that we can do that we're responsible for in terms of reducing embodied carbon? Reuse, reduce, and sequester. So reuse. So the greenest building, development, or neighborhood is the one that is already built. So the first thing we do is look to repurpose urban areas, redevelop, adaptive reuse of existing buildings using local materials. That is the best way to reduce embodied carbon. That gives you huge reductions. And then if we do design buildings, then at least design them to deconstruct them and reuse the materials when their lifespan is up. So first, and now second is reduce. So reuse, now reduce. How do we reduce? Well, creating growth boundaries if we're planners, urban growth boundaries, so we don't keep expanding into suburbs, transportation and roads and infrastructure. If we establish growth boundaries, we can then contain the embodied carbon and look for infill and densification. In pretty much every city, there are huge opportunities for infill and densifying so that we use existing infrastructure. We're not building new infrastructure. We can optimize structure, for example, use less material. And when we do specify and do new construction, specify low carbon materials. And we're beginning to see policies now develop around embodied carbon. And the last thing is sequester. We can actually design buildings that not only reduce embodied carbon, but actually sequester carbon by using wood from sustainably managed forests. And pretty much all of the wood and glue laminated, cross laminated mass timber that we would use in the US comes from northern forests. We're not deforesting. They come from northern forests. They're mostly well managed. They're actually underutilized. And if we're slightly selective, we can get the wood from sustainably managed forests right now. So we want to prioritize that. Use biomaterials when we can, or materials made with renewable energy, reduces their embodied carbon dramatically. And then the other thing we want to begin to look at is site work. Sites and landscaping, and then urban agriculture, actually bringing agriculture back into the cities. These are huge opportunities for sequestering carbon, lowering our carbon footprint. So can we keep the 1.5 degree C alive? Well, I want to kind of go over a little story. There's a story about a courtier who gave a king a beautiful chessboard. And this king asked him, well, what do you want in return for this chessboard? And he said, well, give me 1 grain of rice on the first square of the chessboard, 2 on the second, then double that on the third, give me 4 grains of rice, and then 8, on the fourth, and just double the amount of rice on each square of the chessboard. The king thought about it. He said, that's not very much. That's not very much rice. He said, sure, I'll do that. Lo and behold, before you get halfway through the chessboard with the doubling, which is called exponential growth, you will have exhausted all the rice. The king determined finally that he would have exhausted all the rice in the entire kingdom. So exponential growth is something we're not used to, that we pass over fairly quickly. We're used to linear growth. We get in a taxi cab every eighth of a mile, a quarter of a mile. The amount of fare increases, at a fixed rate. So for example, so it's a linear, essentially a linear process. How we grow, how we age, 1 year at a time. That's a linear process. And that's usually how we think about things. Exponential growth starts out very, very slowly, like 1 grain of rice, and then 2, and then 4, which is almost nothing. And then all of a sudden explodes into explosive growth. Exponential growth is what we're beginning to see now. And that is what may get us to the 1.5. We can see this is world wind electricity generation. You can see the line going out to about 2010, and that's existing. And in 2010, the US Energy Information Administration estimated global electricity generation would roughly follow that gray line, about 945 billion kilowatts by 2021. Well, look what actually happened in 2021. We're at 1,966 billion kilowatts. So world wind electricity generation is growing exponentially. That's an exponential curve with explosive growth. We've doubled the amount of wind electricity generation that happened over time all the way to 2016 in 5 years. And you can see solar even growing faster. In 2010, the gray line was what the projection was back then. What the US projected was world solar electricity generation was 129 billion kilowatts. Today, we're at 1,380 billion kilowatt hours. So the growth has been explosive, and the doubling time is only 2.5 years globally. We can also look at the US. This is US solar, and we can see the same thing, 4-year doubling on average now of solar electricity generation. You can see what the projection was. It was almost nothing. We're way, way, way above, with a doubling time of about 4 years, and I think that will even shrink. And we see US wind generation also exploding roughly after 2010, and is way, way up. So we're seeing explosive growth in renewable generation. Why is that happening? Well, look at the chart on the left. The orange line is solar. This was the price of solar in 2009 and the price of solar electricity generation today. It's past everything. It's the lowest that it's ever been, and lower than any other source of electricity generation. And the same for wind. Wind went from 135 all the way to $41 per million kilowatt hours. So solar and wind have really dropped dramatically, 90% for solar in 10 years, and wind 70%. And you can see what's happening now with storage. Storage is dropping every single year, and it's now becoming competitive. So last year, solar became the cheapest electricity generation in the history of the world. And in 2020, renewable power was the only energy source for which demand increased while consumption of all other fuels declined in 2020. That's amazing. And that's because solar and renewable energy is cheaper now than any other energy source. And that is expected to keep on dropping. Nearly 28 gigawatts of new generation capacity was added now in 2021. We can see that almost 80% of all electricity generation was either solar, wind, coupled with in the dark purple battery storage. So we're really on our way. And if we keep growing and doubling, which we think will happen because new markets for solar are opening up because more R&D is happening as it becomes cheaper and cheaper, and as more people go out and employ solar technologies, we begin to see R&D taking place and new applications opening up, which then increases the opportunities for solar. So we only see an upside to that. So here is the way we think it's going to take place. Look at total generation. This is electricity generation in the US, and you can see it's been flat since 2010. It's actually been flat since 2005, since we issued the 2030 challenge targets. So the building sector is not only bringing buildings in very efficient, but we're reducing our energy consumption and our emissions of the existing building sector every time we renovate. So total generation is now flat. And you can see renewable energy and nuclear, which are non-CO2 emitting energy, producing about 41% of total US electricity generation. That's today, that's actual in 2021. This is what the projections are for 2030 if solar and wind keep growing exponentially. We will see that non-CO2 emitting energy in the year 2030 would be about 69% of total electricity generation, beating our 50 to 65% reduction that we need. And since buildings consume about 75% of all the electricity generated, having it at 69% renewables is going to be huge. And I'll talk about that in a minute. But if we project this out, Biden is calling, the current administration is calling for a totally clean grid by 2035. We see that if solar and wind keep growing exponentially, that's all possible. And we will essentially phase out fossil fuels in the grid by about 2034, a year earlier than the administration hopes for. And we see that happening because the market has taken over. Well, what about the building sector's operations emissions, total operations emissions? This is 2030. We're already down 30%. And you can see that the drop has been mostly in electricity, cleaning up the grid. So we're 30% below 2005 levels. We've already beat all projections made back in 2010, 2015, and so on. And so so going forward, where do we think this is going to go? What are our projections? So we project roughly, because of the electricity grid getting cleaner, a 72% reduction from 2005. And as we transition from on-site fossil fuels, natural gas and heating oil, for example, in the Northeast, then that will reduce, begin to reduce also, so that by 2040, we should easily phase out all CO2 emissions in the building sector. So can we keep 1.5 degrees C alive? We have a huge role to play. And the districts are really the shining light in all of this. And if the districts keep on going the way they're going, we will definitely keep 1.5 degrees C alive, because they're in every major city in North America, and they are providing both the opportunities and showing the way to keep 1.5 degrees C alive. So thank you. I'll now pass on the mic to Vince Martinez, our Architecture 2030's president.